In today's video, we'll go over a brief introduction of vectors. So what makes a vector a vector? Vectors have both direction and magnitude. So for example, our displacement, our velocity, and acceleration are all considered vectors. The equality of two vectors allows us to translate a vector as long as the two vectors are equal and have the same magnitude and direction. This can be seen in figure 3.1, where we can take one vector and translate it and still keep the same magnitude and direction. We can also add vectors as long as they have the same units. So in our figure to the right in 3.2, we see that we can draw vector A and then draw vector B, and if we added our two vectors together, we would get the length of vector R. As well as adding vectors, we can multiply or divide vectors by a scalar. So if a vector is multiplied by the scalar number 2, then our vector will be 2a, meaning that our magnitude is double that of vector A. If we multiply vector A by a scalar number -2, our magnitude is doubled that of A, but its direction is also in the opposite direction. And this can be seen in figure 3.3. There can be multiple components of a vector. So if we look at figure 3.4 and we look at our vector A, you can see our vector A can be expressed as the sum of two vectors. Our vector AX, which runs parallel to the x-axis, and our vector AY, which runs parallel to the y-axis. We can add our AX vector plus our AY vector to get the sum of the vector of A. When dealing with projectile motion, it's important to be able to measure the magnitude and direction of our vectors in the x component as long as in the y component. This can be measured by vector x is equal to vector A times cosine our angle, and we can measure our component y as vector y is equal to vector A times sine times our angle. And this can be seen in our figure below in figure 3.5. Then, if the two components form a right triangle, we can solve for the hypotenuse and find the magnitude of A by taking ax to the square plus ay squared all over the square root will give us the magnitude of A. We can solve for the angle of a vector by taking tangent theta, which is equal to the y component of vector A over the x component of vector A. And this could be used to solve for theta if theta is unknown. So if we look at an example that deals with vectors, we see that we have a hiker that begins a trip by first walking 25 kilometers 45 degrees south of east from her base camp. On the second day, she walks 40 kilometers in a direction 60 degrees north of east, at which points she discovers a forest ranger's tower. In part A, we're asked to determine the component of the hiker's displacement in the first and second days. So we see in our picture to the right, we have the pathway and direction that the hiker took from her base camp, which is marked at the origin in our coordinate plane. In part A, we're asked to find the x and y components of her displacement in the first and second day. So if we focus on the first day, we see that she heads 45 degrees southeast of base camp, which we see is drawn by vector A. So we can find our x and y component if we were to draw a right triangle. We'd see that her x component is in the positive direction, and if we take the cosine of our right angle, we'll be able to find our x component. So the x component of vector A is equal to A times cosine times our angle. So we know vector A is 25 kilometers in length times cosine, and she leaves at an angle of 45 degrees south of east. And if we multiply this together, we'll see that the x component of vector A is equal to 17.7 kilometers. Now we can find the y component of vector A as well. For the y component of vector A, we can take vector A times sine times our angle. So vector A, yet again, is 25 kilometers times sine times our angle of 45 degrees. Our y component is going in the negative y direction. So our vector in the y component of vector A will be a negative 17.7 kilometers. So we found the x component and y component of vector A for the first day. Now we can find the x component and y component of vector B. So the x component of vector B will be equal to the length of vector B, which we see is 40 kilometers, times cosine our angle of 60 degrees. And when we multiply this through, we'll see that the x component of vector B is 20 kilometers. And then to find the y component of vector B, we can see that the y component is made up of vector B times sine times our angle of 60 degrees. And we can draw to help us visualize our x component and our y component for vector B. We'll see that the y component of vector B is equal to 34.6 kilometers. So we found the component of the hiker's displacement for the first and second day. In part B, we're asked to determine the components of the hiker's total displacement for the trip. So what they're asking us to find in part B is the distance from our origin to an x component directly underneath the tower, and our displacement from our x-axis along our y-axis to the tower. So we found the x component of vector A, and then we found the x component of vector B. So we can add our x component of vector A plus our x component of vector B to solve for our x component for vector R. And if we do so, our x component for vector A was 17.7 kilometers plus our x component of vector B was 20 kilometers. We'll see that the x component of vector R is equal to 37.7 kilometers. Now we can solve for the y component of vector R. The y component of vector R will be equal to the y component of vector B, which goes from the tower down to our imaginary dotted line. So we'll have to subtract this distance, and this distance happens to be the same magnitude as our y component of vector A. So we see that the y component of vector R will be equal to 34.6 minus 17.7. And we'll see that the y component of vector R is equal to 16.9 kilometers. Then finally, in part C, we're asked to find the magnitude and direction of the displacement from base camp. So we're trying to find the magnitude of vector R. So we can find the magnitude of vector R because vector R is equal to the square root of the y component of vector R squared plus the x component of vector R squared. And if we plug in our values for our y and x component of vector r, we'll see we'll have 16.9 squared plus 37.7 squared taken to the square root is equal to 41.3 kilometers. And if we are to find the direction of vector r from base camp, we can take the tangent of theta is equal to our y component, which is 16.9, divided by our x component of vector r, which is, and if we solve for our angle, we'll have the inverse of tangent times 16.9 over 37.7. And when we do so, we get 24.15 degrees northeast of base camp.